Okay, so we probably can get it started. As usual, the talk is broadcasted through YouTube in live, so people can also join there. So today we are welcoming Siddharth Mishra Sharma. Siddharth, he works at the intersection between statistics, cosmology, machine learning in general, and he did his PhD at he got his PhD at Princeton University in 2018, if I'm correct. Then he moved for a first postdoc at NYU, and now he's currently he's an NSF AI fellow at the MIT in Massachusetts. And so it's a real pleasure to welcome him here to talk about recent advances in simulation-based inference, which is, I believe, a hot topic in ML, especially applied to physics. So today he is going to talk about his recent work. Before I give the floor to Siddharth, I remind the students if I'm pasting in the chat a link to a Google Doc. So for students that need to register, please just write down your name in the doc, and that will be easier for me to track it down. Okay, so let's get it started. Siddharth, thank you very much again, and the floor is yours.
Thank you, Mark. Thanks for the introduction and invitation. So I'll talk about simulation-based inference, also known as likelihood-free inference, and I'll describe in detail what those things mean as applied to astrophysics and cosmology. And even though I'll try and motivate fairly broadly how these methods can be applied to astrophysics, I'll talk specifically about some work that I am interested in on using these methods to look for dark matter substructure and signatures of dark matter in astrophysical signatures. So before zooming in, before getting more specific, I want to zoom out and talk about what we're doing here. So generally, we think of theory and experiment as like the two big pillars of science. And data analysis computing is also often thought of as an important third pillar. So the way I like to think about things is slightly different, where the two big pillars are models and observations, where observations give us some partial view into reality. And models, on the other hand, give us a framework to understand these observations. And data analysis computing connects these two. And moreover, one of the big things I'll try and motivate is methods like simulation-based inference and advances in computing can transform the way we define models and the way we take observations. But in this case, I'll focus more on how these methods can enable a completely different way to define our physical models. As an example, just to motivate things of observations and models, an observation could be on the right here, observations of the amount of light that's coming from a star as a function of time. And you see this little dip right in the middle here. And the model that we build for this could be a planet transiting in front of the star, blocking out some amount of light and giving us this dip. So connecting this model with observations can tell us something about, for example, the properties of the planet, like its radius, its mass. So by doing this, we're able to infer something about what we can't see using a series of observations. And exactly this interplay between observations and models is what led to a lot of evidence for dark matter accumulating over the 20th century. And one of the crucial pieces of evidence was galactic rotation curves. So these are measurements of the rotational velocity of stars in a galaxy, such as the Milky Way, as a function of distance from the center of the galaxy. And people build models for what you expect this velocity to be. This is just Newtonian. assuming that all of the matter is the visible matter, so things like the stars and the gas in our galaxy. The actual observation pointed to a much higher rotational velocity than what you'd expect with just what you can see, the visible matter. So this led to proposing a new form of matter, the dark matter, which interacts gravitationally. So it affects how things move, how these stars move, but we don't see it. So it doesn't interact with electromagnetism. And since then, there's been an accumulation of a large amount of evidence across different systems and different scales for dark matter, in addition to rotation curves. Also the physics of merging galaxy clusters, the distribution of matter on large scales, the spectral fluctuations of the CMB are just some examples of evidence for dark matter. And one of the hot questions in particle physics with also applications of cosmology is how does dark matter fit into our understanding of the universe? How does it fit into the standard model of particle physics? Is it a particle? As a particle physicist, that's what I go with. So this is the big question that motivates some of the methods in this talk. And today, over the past 30, 40 years, we've built up entire subfields dedicated to looking for dark matter. For example, based on scattering of dark matter against standard model particles, direct detection, production of dark matter in colliders, annihilation or decay of dark matter into visible products in dark matter which reaches the sky. And finally, astrophysical probes, which is somewhat newer and will be the focus of my talk. And the idea here is to use purely gravitational effects to infer the macroscopic distribution of dark matter, and then use that to backtrack and say something about the particle physics properties or the microphysics of dark matter. So the idea here is to go from macrophysics, so the distribution on somewhat large scales, to microphysics, for example, particle properties or contents. So this is, again, the interplay between observations, which could point us to what the macrophysical distribution is, to microphysics, which would be the model that describes the particle physics. And a specific example, which I've highlighted here with good old simulations from Aquarius, is the difference between cold dark matter, which is the standard kind of reigning paradigm with GeV particle masses. And here we expect dark matter down to pretty small scales. And on the other hand, warm dark matter with keV particle masses. So lighter particles, these would tend to be relativistic or faster or on certain epochs in the universe. These can escape gravitational wells more easily. And so they inhibit the formation of structures on certain smaller scales. And a useful quantity to get at this difference is what's called the subhalo mass function or the halo mass function. Halos just referring to dark matter clumps. So these are the little purple overdensities that you see here. And this object tells us about the number of dark matter clumps as a function of their mass. And you can see a difference between cold dark matter, which is the solid green line, which goes down to smaller masses, versus warm dark matter, versus a suppression at smaller masses. So if we could go out and measure the distribution of matter on these smaller scales, that could then let us distinguish between, for example, cold dark matter and warm dark matter models. So that's the basic idea. That's easier said than done. And the reason is the following. On the more massive end, we have things like galaxies and clusters. So we see these very clearly. We can quantify the distribution of dark matter often in these objects quite well. On slightly smaller scales, we have what's called dwarf galaxies. The Milky Way has a bunch of these. These are smaller dark matter halos that still have stellar associations. So as you can see in the bottom right here, they have stars that are bound to them. And we can use the kinematics of these stars to then say something about what the distribution of dark matter in dwarf galaxies is, and what the masses, for example, of the dwarf galaxies are. So we can to some extent quantify the distribution of dark matter using dwarf galaxies in our own galaxy and in other galaxies. The issue is when you get down to smaller scales, where you have more constraining power, you have a bigger difference between, because of models of interest, these dark matter clumps or subhalos tend to be fairly dark and not have much luminous baryonic matter in them. There's not much bound stars, for example. So we can't really see them. And if we can't see them, we can't really characterize them. So the end goal of my talk will be to use some of these methods from simulation-based inference to look for these dark subhalos and try and characterize the population of dark subhalos, both in our galaxy and in other galaxies. So here's a brief outline of my talk. So I'll start with a quick summary of inference in astrophysics. This will be more just how I see it to motivate the rest of the talk rather than something comprehensive. And then I'll move on to two separate projects, which hopefully I'll have time to talk about. The first one on looking for dark matter subhalos in other galaxies using strong lensing. And something I'll try and show is how you can combine information from thousands of different strong lensing systems to build up a coherent model of what's going on. And in the last part, I'll talk about detecting galactic dark matter. It's in the Milky Way with astrometric maps. And I'll talk about what that is. And something I'll try to emphasize here with broader applicability is how you can use some of these methods to extract information beyond some of the conventional statistics that we're used to, like the angular power spectrum, for example. All right, so inference in astrophysics. So here's a cartoon version of how often inference is done. So usually we start off with some data. There's obviously a lot of work that goes into collecting and processing data, but that's something I often don't work on. So I start with data. So as an example, this could be those observations of light from a star that I mentioned here. And usually, as part of our model, we have some parameters of interest that we want to infer. So these could be, for example, the size of the planet or the mass of the planet. And a central quantity in inference is the likelihood function. So this is the probability of the data X being compatible with the parameters theta. And this is provably the most efficient test statistic when it comes to hypothesis testing. So here's just an example in the bottom. So on the left, the model that gives you this bigger dip would have a larger likelihood than the model that gives you the smaller dip. Now, generally, things that sounds easy, but what makes it difficult is we often have these other parameters in the problem in the model called latent variables, which I'll denote Z, that describe other processes that are giving rise to the data generating process that exists, but that we're not interested in necessarily. So for example, in this case, those could be, for example, the natural variations in the light coming from the star, which, if we're interested in the planet, we don't really care about that. So we want to marginalize or integrate over these kinds of effects. So this gives rise to having to do this integral. And often in problems of interest, this integral can be very high dimensional. So there can be many latent variables in the problem. There can be many complex latent processes that are going on, which makes this difficult to compute. But assuming we can compute it, then with the likelihood at hand, we can do inference in whatever way we want. So for example, we can build frequentist confidence sets or obtain a posterior distribution by sampling, for example. So this is assuming we have a likelihood. Now, how can we get around the problem of large latent spaces? In cosmology, there's very well-defined ways of doing this. For example, the CMB, which is a very nice, clean canonical example. The latent processes could be, processes that give rise to individual hot and cold spots. And this is a very high dimensional problem, and the likelihood is completely intractable. But if we assume that the CMB is a Gaussian random field, which is often taken to be the case, then we can, instead of dealing with the full map, deal with low-dimensional summary statistics. So simpler statistics or quantities, or sometimes called observables, that summarize important features in the data. So for the CMB, the canonical summary statistic is the angular power spectrum. So the amount of power contained on different multipoles, describing different angular scales. And it's much easier to work in this low-dimensional domain. We can build theory models using semi-analytic methods. This gives us a tractable likelihood, which can then be used for parameter estimation. So that's the case for the early universe, like CMB, which I described, where you can take things to be a Gaussian random field with quote-unquote linear statistics and summaries that very efficiently compress the data. In the late universe, things can be much more complicated. So here's just some examples of data sets from the Gaia satellite, kinematics of stars in a galaxy, and gamma ray photons from the Fermi satellite. So here you can have much more complex latent processes, nonlinear statistics, and summaries that may not be very efficient in capturing the data. Nevertheless, often the way things are done is by using low-dimensional summaries. So that leads me to the first project that I'll talk about, which is detecting dark matter with strong lenses. And I'll start with a brief overview of what gravitational lensing is. So gravitational lensing is fairly intuitive as a concept. So the idea is light from a source on the right here is gravitationally lensed by some intervening mass, like a dark matter subhalo. So its apparent position shifts in a way that's calculable, that's given by the gradient of the projected gravitational potential. And there's often two regimes that are differentiated in lensing. In the weak lensing regime, when the source and the lens are separated by more than some characteristic scale called the Einstein radius, which I've denoted theta E. We end up with shifts and distortions in the background image, which you can see here. And in the strong lensing regime, on the other hand, where the source and the lens are much more aligned, we get these more exaggerated effects like extended arcs and multiple images of the background source. And in this initial parts, in this project, I'll talk about strong lensing. And in the next part, I'll talk about an application of weak lensing for dark matter searches. So both of these will be relevant. So I'll start with strong lensing. And like I mentioned, the light from background source here is lensed in a way that gives you multiple images of the source in a distorted way. So you get these what's called Einstein rings. And the concept is very similar to the planetary transit example I mentioned earlier, where you have some original undistorted model, and then with the additional intervening object, you get distortion. And because there's a relationship between the distortion and the properties of the intervening object, in this case, the dark matter halo or the cluster or the galaxy that's doing the lensing, we can then infer something about the properties of the lens from observations of the distorted source. So why is it specifically interesting when talking about dark matter substructure or dark matter subhalos? So the idea is the galaxy that's doing the lensing, that is acting as a lens, it's got dark matter subhalos in it. So even though the main galaxy is doing most of the lensing, because it has these little clumps peppered through it, these will cause additional percent level effects on the lens image. So we can use these effects to try and then backtrack and then tell us something about what the population of dark matter clumps in the lens in this galaxy looks like. So that's the big picture idea. And just to illustrate that a little bit further, here's like simulation, a very simplified one. On the left, showing the lensing pattern with just the big host galaxy. And on the right, I've plopped down a little dark matter clump right on the ring. So you see this additional lensing effect right on the ring. And the idea is you can use the fact that you get a bunch of these to try and tell you something about dark matter subhalos. In practice, things aren't that simple. That was a very exaggerated example. In practice, you can't really distinguish the effects of subhalos by eye. So it's a very subtle effect, which is why you have to go into a statistical treatment of it. So this is, again, easier said than done. And the reason is, like I mentioned earlier, because there are a lot of latent variables and latent processes in the problem. So here's an illustration of why that is. So on the left here is my model for the dark matter subhalo population. Here I will parameterize it as a power law. We love power laws with some overall amplitude, which I'll call F sub, which tells us about the abundance of dark matter, and slope beta of the power law. So the goal will be to infer F sub and beta. And our observations are an image without these little confetti dots. So just the image. And we have these latent variables, which are the properties of the source, the lens, and the properties of each individual subhalo. So each individual subhalo's mass and its position. So it's easy to create a simulation. We just, we take our model, we draw some random latent variables like masses that are consistent with this model. We put them down, run our ray tracing code, and get an image. Going the other way is much harder because we have to integrate over all of these different possibilities. We have to integrate over all of the different possible positions of the subhalos and all possible masses that subhalos could have. So this is a huge latent space, which makes the problem difficult. And this is the big challenge for inference. The way people attack this traditionally is, instead of looking for this whole population, look for individual subhalos. So like that example I had earlier with the big subhalo on the ring. So in this nice paper by Hazavi et al. From about 5 years ago, they used observations from ALMA, interferometric observations, to look for individual subhalos near the ring. They found one of 10 to the 9 solar masses and used this to place constraints on the halo mass function, the subhalo mass function. The downside is, because you're looking for subhalos that individually have a big effect, you can only really be sensitive to the higher end of the subhalo mass function. Whereas the more interesting part, which is lighter subhalos, which individually don't have a big effect, but collectively can do something interesting, those are harder to tease out with these kinds of methods. So the goal of the project that I'll talk about is to enable scalable inference of subhalos across a large population sample of lenses. So right now, we don't have a ton of strong lenses, maybe orders of 50, depending on what kind of fidelity you want. But in the future, with observatories like Rubin and Euclid, we expect large samples of galaxy-galaxy lenses, so orders of tens of thousands and even hundreds of thousands. And And these will contain within them effects of dark matter substructure. So the idea is to have methods that can capture, going back, that can capture all of the information from high-dimensional data, that can scale to a large sample of lenses, and can deal with this issue of a large latent space. So that brings us to simulation-based inference. Some of these slides were inspired by my collaborator, Johan Bremer. And the idea here is if you have a class of models where you have some physical model for how the parameters are related to observables, you have a simulator that can generate samples from your parameters, but going the other way around is hard. So computing the likelihood is challenging. So these are exactly the classes of problems that simulation-based inference aims to solve. So there's traditional, this isn't a new field, there's traditional ways in which SBI, simulation-based inference, has been applied. The most common is a class of methods called approximate Bayesian computation. I won't go in detail through the schematic, but the idea is you produce observables from your simulator, reduce this into summaries, compare these summaries with your observation. If they lie within some threshold, then you accept your parameters, and you repeat this many, many times to build up a posterior distribution. There's several issues, which is some of which are you have to choose a summary statistics, so you can't directly work with high-dimensional data because that's inefficient. That's the curse of dimensionality. Reducing data to summaries means you're losing information. You have to have some way of comparing your summaries with what you data, some kind of distance metric, and the likelihood may not be well motivated. And then every time you have a new data set, you need to rerun this pipeline anew. So for example, in the present problem, if we have thousands of lenses, that's not very efficient. So there's lots of recent progress in dealing with this using techniques from machine learning. And if you're interested, I'd encourage you to see this review by some of my collaborators in PNAS. So the question we asked a couple of years ago with Johan Bremer, Kyle Cranmer, as well as Joey Hermans and Gilles Loup, who are in Belgium, is can we do better for the strong lensing substructure problem with machine learning? So we have good simulators which describe full physical models with interpretable parameters. And these days we have machine learning techniques that can learn efficiently from high dimensional data sets and can efficiently approximate functions and distributions. So can we combine these two in a nice way? So this is very different, I want to emphasize, from a more traditional application of deep learning or machine learning, where you might imagine you train some computer vision model to give you estimates for your parameters of interest, your slope and your f-sub amplitude. These kinds of applications early on, I think gave machine learning a bit of a bad reputation in the physical sciences because it's not clear what to do with such point estimates. There's no notion of uncertainty. There's no notion of statistical significance. We tend to be pretty rigid about, how significant is this? We're not clear how to combine these estimates across multiple systems. So this is something that simulation-based inference can really attack very, very efficiently. So there's many different methods to try and get things like likelihoods and posteriors and likelihood ratios from high dimensional data sets defined by simulations, in models defined by simulations. Here I'll use just one of these based on what's called a likelihood ratio trick. And the idea here is the following. So for example, we have a simulator that can produce samples from two different hypotheses in our model. So for example, samples based on theta 0, f sub 0, and theta 1, f sub 1. And if we have a classifier that can be trained to distinguish between samples from these two different hypotheses, the optimal classifier, which gives you a probability between 0 and 1, is this one here, which is 1-to-1 with the likelihood ratio between theta 0 and theta 1 hypothesis. So that's kind of the basic idea, is if you have an efficient classifier, you can then turn that into a likelihood ratio. And the reason the optimal classifier is 1-to-1 with likelihood ratio, again, comes back to the fact that the likelihood ratio is the most efficient test statistic, which is an old result from statistics called the Nyman-Pearson lemma. So this, on the face of it, seems very inefficient, because it seems like now you have to train a whole new classifier, which in our case could be a neural network, for every pair of parameter points. For every pair of thetas, theta 0, theta 1, you have to train a new classifier. That's obviously not efficient or tractable. So what's done is this denominator hypothesis, theta 1, is fixed. And you can fix this because it doesn't actually matter what this fixed hypothesis is. You can get the ratio between any two hypotheses by just taking the ratio, and then the theta 1 likelihood cancels out. So that can be fixed. But now again, it seems like you have to train a classifier for every possible theta 0, or every combination of beta and f sub. So to get around that, what's done is the dependence of theta is put into the classifier, or into the neural network in our case. So now the classifier is parameterized by theta, and we have a parameterized classifier that acts as an estimator for the likelihood ratio. And now when we have a new data set, we can put that in, scan over thetas, and that can give us the likelihood ratio in our parameter space. So what we did is we tried to apply this to the strong lensing problem. This is very much a proof of principle. These aren't very realistic simulations. But just to show that this is something you can do, we simulated an ensemble of lenses according to parameters, observational parameters from based on Euclid. So these are just some examples. The confetti dots are the positions of the individual subhalos. And our fiducial point that we tested on corresponds to a substructure fraction of 5%, and a slope of minus 0.9, which is roughly what you expect in lambda CDM. So we put down galaxy sources at about a redshift of 1.5. We put galaxies varying the redshift between 0.5 and 1. We peppered our images with subhalos from the mass function. And we used a machine learning architecture from computer vision, the LeVesnet, which is a convolutional neural network that is very easy to just get off the shelf. So there's nothing customized with the architecture here. So a schematic of training the likelihood ratio estimator. We take a parameter of interest, pipe it through our simulator, produce observables. These are used to train a classifier based on this convolutional neural network that's parameterized additionally, as shown by this arrow, by the parameters of interest. And this can be used as an estimator for the likelihood ratio. Now, what this lets us do after training is, given a new image, we can build up the parameters of interest for a given the likelihood ratio surface for a new image. And now we can do hypothesis testing in any way we want. Again, like building up frequentist contours or drawing samples to build up a posterior, for example. So here's an example of that. After training, on the left, we have our new image that the network has never seen before. And on the right is a heat map of the likelihood ratio with the true parameter point denoted by the star. And the 95% contours are shown in black. So you can see, first of all, the true value lies within the contours, which isn't that impressive because the contours are very wide. But now we can look at a few different lenses to see what's going on. So on the very left, we have like a low fidelity, a small lens. This might not have much substructure in it. The substructure that it has doesn't have a lot of area on the ring to kind of express its effects. So we end up with a flat likelihood surface. So this is saying there's not much information of interest in the image. Going to the rightmost image is a much more high fidelity image. In this case, we have a bigger halo with a brighter ring. And now we have better constraints on the mass function parameters of interest. So the nice thing here is once you've trained your network, you can apply this to a new data set very quickly. So you don't need to go through the whole analysis every time you have a new data set. You can just train once, you've given some upfront cost, and then things are quick. So because we're dealing with likelihoods, which are very nice objects that can just be multiplied together, or the log likelihoods can be added together, we can combine information from multiple lenses. So on the left, I'm showing the same parameter space, f sub and beta, combining information from 5, 20, 100 lenses. So you can see that the expected frequentist contours get tighter and approach the true value in an unbiased way. And the right is just showing a slice through beta equals minus 0.9. Again, you can see that the likelihood the surface gets tighter as you start adding more and more lenses. So this is the final slide of this part of the talk. So again, because we have a likelihood, we can do Bayesian inference over a big sample of lenses. So I'll show a small video here where on the left, I'll add more and more lenses into my sample. On the right will be the posterior on beta and f sub, our parameters of interest. And in the middle will be the corresponding mass function inferred from those samples. And the dotted line here is the true underlying population point that these were simulated from. So I'll play this forward. You can see that initially the mass function is very poorly determined. But as you start adding more and more lenses, you start getting tighter and tighter constraints on the mass function. Eventually, after adding hundreds of lenses, you get close to the true value, again, without any obvious biases. And the last thing I'll mention is the code to reproduce this full analysis is available freely on GitHub. All right, so that brings me to the last part of my talk, which will be much shorter. I don't think this will take more than 10 minutes, which will be based on detecting galactic dark matter substructure, so subhalos in our own galaxy with astrometry. So astrometry just refers to the measurements of positions of celestial objects very, very accurately, in a way that we can get distances to them as well as motions, so velocities and accelerations. So typically these measurements look like this. So the black lines are measurements of the positions of a star that this is just a cartoon version. And you see some overall trend, and this tells us about the overall the velocity or acceleration or the drift of the star. And this loopy structure is because of the parallax, so the motion of the Earth around the sun, which tells us something about the distance of the star. So velocity, mu alpha, and parallax, omega. And the state of the art in astrometry is the Gaia satellite, which has so far imaged over 1 billion stars with better than milli-arc-second precision. And just for fun, this is a very exaggerated version of actual Gaia data from DR2, their second data release. of nearby stars kind of propagated forward in time according to the measure velocities and parallaxes, and you can see exactly this kind of loopy structure in many of the stars. All right, so why is this interesting for galactic subhalos? The idea again is very similar to what I said before in the previous section. If we have subhalos in our galaxy, their apparent positions would be shifted due to gravitational lensing. And we can go in and calculate what the expected magnitude of the shift is for a typical galactic subhalo. And this would be of the orders of hundreds of micro arcsecond. Now this seems tiny, and it is very tiny, but it's actually well within reach already of satellite like Gaia. So here's an illustration of this effect. For example, we have a grid of stars, and we plop down the subhalo right in the middle. The apparent positions of the stars, especially closer to the subhalo, subhalo is the white object, are shifted. The problem, though, is that we don't know what the true positions of these background sources are. So if we see something like this, and the true positions are in green, we can't really say anything about what's going on. So here I've put down the subhalo again in the middle. You can't see the subhalo, but we can't really use positions to look for lensing effects. And just another way of saying this is that the natural variations in the number density of background sources, which can be either stars in our galaxy or other very far away galaxies themselves, the natural variations are bigger than the size of interesting effects that you can have. So even though you can pin down their positions very well, you can't use this to backtrack and talk about lensing effects from subhalos. A potential solution is to instead look at velocities. So the idea here is subhalos in our galaxy are not stationary. They move with some velocity dispersion. And as they move, they cause a time-dependent lensing of background stars. So here's just an animation of that effect, a very exaggerated one. But the idea is if you take a snapshot of this at any point in time, you would see the stars moving in a correlated way. And this is something you can use to look for dark matter substructure. This general class of methods were proposed by some of my collaborators back at NYU, Ken Van Tilburg et al. And so we can calculate the shift in position by taking a derivative. We can calculate what the expected velocities of these stars would be. And if we again do the exercise of computing what the typical size is, it would be of the orders of 10 to the -3 micro arcsecond per year. Now, this is very tiny. This is smaller than anticipated precision by any even futuristic observation. But something we can do is rely on the fact that you get correlated effects. So these effects don't show up individually on each star, but on the other hand, if you have a subhalo, the stars around it will be moving in a correlated manner. This is especially easier as most things are for more compact subhalos. So if you have very point-like sources, these can have bigger effects. So this is illustrated on the left. If you have a bigger subhalo, like a more fluffy subhalo, as expected in CDM on the right, the effect is smaller. And this is because at a given distance from the center of the lens, for a more extended lens, there's less mass contained within that radius. So M of B is smaller. So in general, you have smaller effects. Just to illustrate what this signal looks like, if we go back to the grid I had at the start of this section, this looks like a dipole. This kind of looks like a magnetic field pattern. So if we have a bunch of these subhalos in the sky, what we should expect is a bunch of these little dipole-like patterns on the background stars or galaxies whose velocities we're measuring. And moreover, if we have a whole population, there's again correlations between these. So the hope is to try and use these correlated effects over large regions of the sky where we have populations of subhalos to then try and infer what the properties of the population are. So this is again very similar to what I said in the last section with strong lensing. We have the model. Here I'll just parameterize it as an overall amplitude without a slope. We have our astrometric maps, which are the 2D position angular velocities in the sky of the different stars. It's easy to simulate, but it's hard to go the other way around because of this large latent space, which in this case would be the positions and the masses again of the subhalos. So something we did about a year ago with former collaborators at NYU. And the first thing we think of as astrophysicists and cosmologists when we see a data set over some large regions of the sky is to use an angular power spectrum decomposition. So this simulation at the top is an example of what the signal might look like over the entire sky. So you can see these little dipoles, which is how the signal expresses itself. And if you decompose that into a power spectrum, and because the signal is in vector in this case, you need to do a vector power spectrum decomposition. You can try and look for the signal above noise. So we did this, and we did some sensitivity projections for what kinds of populations you can infer with this kind of power spectrum technique. So this is a plot of the reach of SKA. In red, WFIRST formerly, the Nancy Grace Roman telescope, in blue, and Gaia by the end of its mission. From parameter space where the subhalos are often given mass and size, assuming NFW subhalos. So this is already interesting because you can detect relatively extended subhalos. More traditional methods based on micro lensing, for example, that are very good at looking for example, primordial black holes, very point-like objects. They can really look for very point-like objects. But here you can already start getting at more diffuse and fluffy objects because you're exploiting this correlated motion across the entire population. When it comes to looking specifically for a cold dark matter population, on the other hand, things were not as optimistic. So this is a plot that's a little bit maybe hard to interpret, but this is a heat map of the discovery significance as a function of, on the x-axis, the number of background objects that you can measure, and on the y-axis, the precision with which you can measure the velocities. And you can see the 1, 3, 5 sigma contours. And a future survey, so SKA, after 10 years of running, can only really get us maybe somewhere in this green region here. So the takeaway is that a CDM population is hard to detect using a power spectrum with these kinds of observations. So something I've been thinking about recently that's work in progress is using higher order statistics. So going back to the CMB, for example, this is very close to a Gaussian random field. So you can extract a power spectrum with little loss of information. The signal in our case, as you can clearly see, is very non-Gaussian. So when you're doing this reduction to summaries, you're losing information. So the question I asked is, can we use some of these simulation-based inference techniques based on machine learning to extract more information? And can you get close to the CDM parameter point with some of these more advanced methods? So here's an illustration of the method and the architecture. The details aren't very important, but I'll just give a very brief overview. So on the left are the maps that are input. These can be the training data or later on the actual data. And the architecture in this case is not like an off-the-shelf convolutional neural network. So in computer vision, for example, they're very good at dealing with rectangular images. These are the kinds of standard dog versus cat applications that you see in machine learning. In this case, we have data over the full celestial sphere. So in this case, we use an architecture based on spherical convolutional neural network that works over helix grids and can then coarsen the data at different scales to look for structure at different scales. And then again, uses this classify approach to estimate the likelihood ratio. So here are the results of this kind of analysis. So in blue, you see the results using the power spectrum that I mentioned earlier, using different cutoffs for what your largest scale is that you use. The idea is large scales are generally dominated by systematics and cosmic invariance. So these aren't really usable in practice with the power spectrum. So you can see these in blue. And the approach with simulation-based inference is in red here. So you can see that you can start getting sensitivity, starting with just 2 sigma, but significantly better than the power spectrum approach with this what's labeled GCNN, which is a graph convolutional neural network. And on the right here is the scaling of sensitivity with the instrumental noise. So again, you can see that the scaling with the machine learning-based approaches is much more favorable as you go to larger instrumental noise compared to the traditional approaches based on the power spectrum. And this kind of generally true empirically. When the signal to noise is low, when you have larger noise, machine learning methods tend to be disproportionately better compared to traditional ones in extracting kind of the last ounce of information that you can from these maps. Now, some of these gains might not seem super significant. It's not like you're doing an order of magnitude better than the traditional approaches based on summaries. But these gains of sensitivity can translate to many, many, many years of running a telescope for observation. So the way I like to think about it is not in terms of like you can do better by a factor of 3 or 5, but you can get many years advantage when it comes to running a telescope, which is expensive by using some of these methods. All right, so that brings me to my last slide. I've talked about dark matter and some of the projects that I worked on, but I just want to emphasize that these methods are very widely applicable in astrophysics and cosmology, and I just wanted to highlight a couple of recent examples, and also showcasing how you can directly connect models to observations using some of these methods without having to go through intermediate handcrafted summary statistics. So something that's been getting a lot of interest is analyzing gravitational wave strain data with some of these methods to get out for example, merger parameters, analyzing light curves and microlensing, exoplanet studies. And for example, in cosmology, analyzing weak lensing convergence maps and even distributions of galaxy clustering, for example, to get much tighter constraints on cosmological parameters that you can with traditional summaries. So that was just to give a flavor that these methods are really widely applicable. And some of these have to do with image data. My initial example was image data. The second example was pixelized data on the sphere. Some of these other examples are time series data. So these methods are very widely applicable across different types of and formats of data sets and data domains. And that brings me to my conclusions, which is just to say that some of these methods do have the potential to revolutionize how inference is done in astrophysics cosmology. They can be used to capture the maximum amount of information from high-dimensional data sets, can be scaled to large samples of data, can be used to do real-time parameter estimation. So you don't have to go through the whole process again. Once you have a trained model, you can apply it very quickly to any incoming data set, and they're widely applicable across different types of data. So that's all I had to say. And thank you guys for listening. Happy to take any questions.
Thank you very much, Siddharth, for this enlightening talk. Wonderful. I have a few questions on my side, but I don't know if the audience wants to start or ask any question. Please, you can raise your hand and ask questions. I see one hand. Yes, Andres, please go ahead.
Yeah, thank you, Siddharth, for the talk. I'm wondering, so because you have shown examples of applications of this likelihood trick to low-dimensional spaces. So apart from the latent space, the inference is really happening on 2D or 1D. How does this scale with dimensions? So can this be applied easily just by introducing that on the neural network at a large scale? And then once you train that, how do you sample? So do you need MCMC to sample from the likelihood?
Yeah, that's a really great question. So the examples I've showed, the first one uses two parameters, beta and f sub. The second one's a single parameter. So these are very low dimensional parameter spaces. And in the first example, I showed some how you get a Bayesian posterior and there you don't really even need to sample because you have two dimensions. You can just scan in beta and f sub, and you can get your posterior. In higher dimension, absolutely, these methods are applicable. But once you do inference in high dimensions, you can't do what I did. You can't just scan in your parameters, obviously, because the dimensionality explodes. So there, yes, once you have a trained model, you can then go in and sample from the model. And there've been efficient methods proposed to do this. There's some nice ones by my collaborators, Gilles Loup and Joey Hermans, based on, once you have a trained model, you can do Hamiltonian Monte Carlo on it because everything is kind of differentiable. So you can work with the fact that you can compute derivatives of everything basically to then sample from these high dimensional parameter spaces. So that's the case with this class of techniques based on the likelihood ratio trick. There are other classes of techniques, for example, based on normalizing flows, which are also very popular and which I'm excited about and I've been using as well in recent work. And there things are easier because it's very efficient to sample in high dimensional spaces with normalizing flows. So there, they have there's no one size fits all method. These methods tend to be better. In my experience, for example, when you want to combine things over many different data sets, you really want to fine grain notion of how the likelihood changes in your parameter space. With flows, because it's based on transformations, it's a little more complicated, but it is easy to sample from. So for example, if you have a single data set in a high dimensional parameter space, that can be more straightforward because you just train a model and then you can sample very efficiently.
Okay, thank you.
Thank you. There's another question on the chat that I can read from Natalia. She says, "Thanks for the talk. I'm wondering there are already any studies based on the Milky Way galactic lensing using Gaia data, or is just a proposal?" Maybe I missed something.
Yes. No, that's a great question. There are. I didn't mention these because I was focusing more on the machine learning application. But some of my collaborators at NYU they've come up with techniques to do these studies with some simplified observables. And one of these is based on templates. So when you have a population of stars, if you put down a subhalo at a given point, you know exactly how it's going to affect the velocities of the nearby stars. So what you can do is build up a template or a matched filter essentially for this expectation, and then run it across the sky. And then when it lights up, that's saying that you have some high overlap between the template and the data, and that could point to there being a subhalo there. So there's a paper. I don't think I have it in my backup slides, but it's by Ken Van Tilburg, Christina Mondino, Anna Maria Taki, and Neil Weiner, that does this kind of matched filter analysis using stars in the Large Magellanic Cloud as background. So they look at the stars in the LMC and they run their matched filter on these stars to try and look for the effects of subhalos. And they're able to put constraints on a population of subhalos or rather compact objects. The constraints in that case are not super strong, but are expected to improve rapidly with further data sets. So that was just a proof of principle to kind of show that this is very much possible. This isn't just like a proposal, but that was using Gaia DR2, and I know they're working on analyses that can get much better constraints with DR3 and beyond.
Thank you. Is there any other question? No. We are already running a bit above the hour. I just have a quick question. I have several, but one regarding when you have your simulator from which you create the data to estimate the likelihood radius. Then this is based, again, it's only based on simulation. So when you go to real data, you still have issues of especially when you're using neural networks of domain transfer issues, right? You need to be sure that your simulator is properly capturing all the data details, especially dealing with images. And so from what you've shown is essentially you have proved that it works when you work on simulation, but when you go to real data, you know how these propagates into the error budget, or there's a way of quantifying these? For example, if there's some domain gaps between your simulation and your data?
Yeah, that's a great question. That's, the kind of common concern when using some of these machine learning methods is how do you make sure you're not messing up something in the domain transfer. I think one thing to keep in mind is what you're comparing against. So if you're using some of these traditional methods, they can suffer from some of the same issues. So this isn't something that's specific to machine learning, although I will acknowledge that with machine learning, because you're extracting more information from the simulations, they can be more sensitive to some of the more specific features that you've put in. That if you're using summaries, you've kind of coarse-grained over the data, and you might have less sensitivity. So that is definitely an issue. I'm not an expert definitely on this. I know Kyle Cranmer has worked, and his collaborators have worked on some methods on using adversarial methods to try and account for systematic differences between the simulations and the real data. And because we're working in, again, these likelihood domains, you can actually quantify, where in your learned data space, your probability space, the real data lies, and if it's like very far away and gives you a terrible likelihood, that's maybe telling you that you're not describing the data in the right way to simulations. So there's certainly ways of doing it. Yeah. But agreed, this is definitely a concern when applying to real data.
Yeah. Thank you. I don't know if there are no more questions. I think probably it's time to close the session. I really would like to thank you again, Siddharth, for this very nice talk. So the talk has been recorded, so it's available online for everyone. And thank you all for attending, and see you next time. Thank you.
Thanks, everyone. Thanks, Mark.